Welcome to part 7 in the multiple regression series, the second to last installment, where we look at what's called interaction. So obviously in this video, you'll learn what an interaction is. We'll see how to incorporate interaction into models containing one categorical and one numeric predictor, as well as models with two numeric predictors. So an interaction is something that takes place between two predictors. So that is the relationship between one of the predictors and the response is different depending on the values of the other predictor. So here's an example. Sometimes students might be familiar with what are called drug interactions. So for instance, for some people with high blood pressure, taking medication helps to lower their blood pressure to a healthy level. Okay, so imagine we start up really high here. They've got really high blood pressure. And in the absence of grapefruit, their blood pressure decreases slightly down to a more healthy level. So we have a line here, imagine kind of traveling from this higher blood pressure down to this lower one. However, certain medications, their effects are actually enhanced by grapefruit. It makes them kind of work in overdrive. So blood pressure, that same blood pressure medication plus grapefruit, all of a sudden the blood pressure drops precipitously to a dangerously low level. People can actually pass out, or in severe cases, they could die because of the interaction between the drug and the grapefruit. All right, so the change in the blood pressure is different depending on this other thing, depending on whether or not someone ate grapefruit. So we can build models that include this new potential interaction between predictors into our model. And this is done by adding a term where x1 and x2 are multiplied by each other. So the product of those x's will get its own beta coefficient. Everything else here looks the same as what we're used to. We have an intercept, a beta coefficient times the first predictor, beta coefficient times the second predictor, and the random error at the end. So this is your introduction to interaction. We're only going to consider two factors interacting. It is possible to have three or more even predictors interacting, in which case you'd have like x1 times x2 times x3. But those get very hard to kind of wrap your mind around or interpret. So we're going to stick to two. So since we have an x times another x, it's kind of like, not exactly, but sort of like x squared. So like in what we call a quadratic model, where we actually do have a true x squared, we consider both of those second order models. Okay, so a first order model just has plain old, beta coefficient times an x plus another one plus maybe some more. But in our second order model, we have x's being multiplied by themselves or by each other. So we'll start with an interaction between a numeric predictor and a categorical predictor. So we'll go back to the FEV example, where we're looking at the forced exhalation volume of teenagers. And we found before that there was a difference between males and females when it comes to their FEV. And we also saw that height played a role. But let's see if there's an interaction between height and sex. So we'll also add in a third term. All right, so I'm going to jump. We'll fit our model. FEV is the response. Now to get this interaction model, first add the individual predictors. So we're going to use the height, and we're going to use the sex dummy variable. To get the interaction, we want to multiply these two things by each other, or as we say, cross them. So pick one of those things up on the top left and the opposite one down below. you want to have one of each. It doesn't matter who's picked on the left and who's down below, as long as they're both highlighted. So just arbitrarily, I'm going to pick height on the left and sex dummy on the right, and I'm going to press cross. So now we have those two things multiplied by each other. Just like in our model, we said we wanted x1 times x2. So there it is. And then we can run. Okay, so what do we see? We see a regression plot where we have two lines of fit, one in gray. So remember, the gray was the sex category that was assigned the zeros. So that's the females with the gray line. And then the other one was for the males with the red line. So what do you notice? These lines are not parallel anymore like they were previously when we did not include interaction. So allowing for interaction allows the two groups to have different slopes to their lines and different y-intercepts too. All right, and this maybe looks like a better fit because remember we had said with the parallel lines, we kind of saw that it didn't really describe the higher end males very well. They seem to be quite far above the line. Okay, I think I have side by side. There we go. All right, so our first order model where the two sexes were forced to have the same slope look like this. But if we let them have different slopes by including interaction, it looks like the female slope is a lot lower than the males. They're both increasing here, but the males are increasing at a much higher rate. All right, so among the females, there's a slight positive relationship between height and FEV. It goes up a little, but between males, it's a much more noticeable rate of increase. Okay. So in other words, the relationship between height and FEV is different for the two sexes. So it depends on whether someone is male or female if we want to make a good prediction. So that's what we mean by interaction. The relationship between this one predictor, height, and the FEV is different depending on what the other variable is doing. All right, so we can do a hypothesis test to determine if the interaction is significant between these two variables. So we'd be testing the third beta coefficient here, the one that was associated with x1 times x2. And the null hypothesis is that our two variables do not interact. If that's the case, then the coefficient here, the true value would be 0. This, of course, is just an estimate of it, but in the population, it would be 0. Alternatively, there is some kind of interaction between our two predictors. So beta 3 does not equal 0. So the t, it's a t-test, like our other tests for coefficients that we did a few videos ago. So the t ratio is our test statistic, and then the two-tailed p-value, we'll always use the two-tailed p-value for interaction, is right here, so 0.0034, which is pretty small. So we can reject the null hypothesis and conclude that, yes, there is a statistically significant interaction between height and sex, which is to say the height and FEV have a different relationship for males and for females. All right. So we're just learning about interaction now, and we're 7 videos into this topic. So you might be asking, well, should we have been including interaction this whole time? So think about for your two variables, is there any reason why they might kind of influence or have some interplay with each other? So we know that males and females are different for a lot of things. So maybe it could be for the relationship between height and FEV as well. So you can always try it out. If you find that it's statistically significant, then you should keep it in the model. It's a significant predictor. If you keep it, keep the individual predictors as well, even if they don't seem to be significant on their own. So here's a good example. The interaction was significant, so we know we want to keep that in our model. Well, it's the product of x1 and x2, so we should keep those as well, even though the height looks like it's not particularly important here. Okay, but we know that kind of it is, because when we fold it into the interaction, it is important. So we'll keep both. All right. So remember, in the previous video, we also looked at whether the smokers versus the non-smokers were significantly different. So maybe we missed an interaction there. Well, I fit a similar model with height and the smoker dummy, and it looks like that was not statistically significant. And it wasn't even really close. You could argue that if it was, say 0.10 or so, maybe you'd keep it because you're getting closer and closer to 0.05, but over 0.5, definitely not very useful. So we would get rid of that, and that would free us up to, we'd see how these p-values change, and then we may or may not consider getting rid of the smoking dummy variable, depending on, R squared and root mean square error and all those things. All right, so the prediction expressions get a little trickier here. So here's the kind of general form of the prediction expression for an interaction model. So the B's, the B0, B1, B2, B3, those are the estimates in the parameter estimates table. So here our intercept B0 is 1.014. Then we have our second estimate times x1, which is the height. So here, 0.031 if we round, times the height. Then we know we have to do the matching. So here's our dummy variable, our on-off switch, if you will. So if it's, the coefficient is 0.714, so that's going to be multiplied by 0 if it's a female, so essentially it'll disappear, or multiplied by 1 if it's a male. So this part will show up for the males, but not the females. Then we have our last estimate, about 0.113, and that'll get multiplied by x1 times sort of x2 in this case. So x1 was the dummy, or x2 rather, was the dummy variable. So we have the 0 or the 1, and that gets multiplied by, you would think height. Jump actually does something special. It recenters the height. So this number here, the 66.8496, that's the average height of all the people in the study. So it's just a standardization process. All right, so that would be the same for both sexes here, but because we have the 0 and the 1, the females really, it's just not going to show up here either. So let me do a couple predictions to illustrate. All right, so for a female, we'll start with the intercept. Everybody gets the intercept. We'll add in 0.031 times the height, and her height is 66 inches. And then kind of looking ahead, well, we'd have this coefficient times 0. So I could write it in, but let's just say plus 0. And then over here, we'd have 0 times her height minus the average height. Well, that'll be 0 times the coefficient, still 0. So it's kind of like plus another 0. All right, so the predictions for the females then are not that bad. So this is 3.06, and the units were FeV in liters. For the males, we have a little more work to do. So it'll start out the same way, and this guy is also 66 inches tall. The first two terms will be identical. Then we get to this term here. So we will have the 0.714 times the 1. So essentially the 0.714 will show up. And then we'll have 0.113 times 1, because it's a guy, times the height, 66, minus the average height. Okay, so just remember your order of operations, do all your multiplications before you add up the 4 parts. So if you have everything in the right spot, this should be 3.678 liters. And just comparing, does that make sense? They're the same height. We saw previously that it looked like males tend to have the higher FEVs in general. So his FEV is a little higher than hers. And we could peek at the graph and just see, yeah, those seem reasonable based on where those lines were. All right. Our coefficients in a second order model are no longer, strictly speaking, like partial slopes anymore. So in our old model, we could say that the coefficient, say, attached to height would be how much we expect the FEV to change as height goes up by 1 inch. But notice height shows up again. So it's not always going to be that way. Now for the females, since this sort of disappears and this sort of disappears, then yeah, I guess for females in this case, that would be the partial slope for them. But it's not universally true because the males we see have a steeper slope. Okay. So I won't ask you what the slope would be for the males. Don't worry about it. But we can clearly see it's going to be steeper. All right, now let's think about the interaction between two numeric predictors. Let's go back to our classic example, the grandfather clocks. And we'll include a interaction term there between the age and the number of bidders. So that's where we have x2 and x3, x1 and x2 multiplied by each other. And they get a new coefficient, which is beta 3. So analyze fit model. And we want x1 and x2 down below, y up top. And then don't forget the interaction term. So pick one of them down below, doesn't matter which. Pick the other one off to the left and press cross. So, we just added interaction. Was that a good move? Let's find out. So is it a useful model? Just mention in passing, the residual by predicted plot looks good. The F ratio in our test is very large. The p-value is very small. So this is a highly useful model. And looking at our parameter estimates, all of the predictors, including the interaction, are statistically significant. We got some really big t ratios here, so that's really significant. So it looks like it was a good move to include interaction in our model. A few other ways that I can tell. You may have remembered that the residuals, when we did the grandfather clock example the first time, they were a little non-normal. I kind of said, well, this is a good starting point and we'll try to improve this later on. So here's the improvement. Shown here are the residuals from this new model that does include interaction. And they look a a whole lot more normal than the original first order model where we just had age and bitters. All right, so if you notice your residuals are not normally distributed, maybe they're bimodal or really skewed or something, that might be a clue that something is missing from your model. So here, the missing piece was the interaction term. Let's, with our FEV example, we could see the two lines with different slopes. So we got a visual of what did an interaction represent in that case. To get a similar view for two numeric predictors, let's go to our model output and under factor profiling, we're going to look at the surface profiler. Back on my clocks. It's the very top red triangle, factor profiling, surface profiler. So remember, we looked at this the first time we did the grandfather clocks. We saw we had this cube and we could grab it and spin it. In the first order model, what were we spinning around? It was just a square, a flat plane. Here with our interaction term, we can see it's curved. Reminds me of like a tarp that you would use over like a picnic table or when you're camping or something. So see, it's got some bends to it. So the slope along one edge is not as steep as the slope along the other edge. So it's kind of like we saw the two lines with different slopes. Well, now the edges of this surface have different slopes, and there's a continuous blend in the middle as we go from one to another. All right, so it's a lot to think about. We have this whole topography here. Let's go back up to the top red triangle, go to factor profiling again, and this time pick interaction plots. This will help us, visualize the interaction. If it's a little small, you can grab it in the corner and make it bigger, easier to see. So what's going on here? We have our two variables arranged in a little matrix. So age of the clock is going to be on the x-axis in this lower graph, whereas age of the clock is going to be on the y-axis in the top graph. All right, so let's stick to the bottom for now, the bottom left. So along the x-axis then is the age of the clock. We saw the clocks ranged in age from a little over 100 up to a little under 200. Then it's going to draw lines for the two extremes, the minimum and the maximum for the other variable. So that's the number of bitters. Our number of bitters ranged from 5 to 15. So these are the kind of the most different that the slopes could be. So if we held the number of bitters constant at 5, this would be the rate of change between the age and the price. So it's a more gentle slope there. So for five bidder auctions, the price does go up with the age, but not as steeply as it would go up if we had 15 bidders. So when there's more bidders, the rate of change between the age of the clock and the price is greater. Imagine like an auction where everyone's going crazy over this really old clock. I guess it's like that. All right, if we think about it the other way around from the other perspective, so in the top right graph, we'd have the number of bidders on the x-axis, ranging from 5 off to the left to 15 on the right. Then the two lines here represent the minimum and maximum age of the clocks. So for the youngest clocks, we see a kind of a gentle slope here. So there's a positive, slight positive trend. That is, the number of bidders goes up, the price goes up. Whereas for the really old clock, as the number of bidders goes up, there's a much steeper rate of increase in the price. So they really, these told us the same thing. It's just which way do you want to look at it? All right. So when we have these two numeric variables, two numeric predictors, the prediction expression is going to look like this. So again, we have four coefficients. Well, the intercept and three coefficients. So the intercept off by itself. Then we have the first estimate times the age. Then we have the second estimate times the number of bidders. And then we have the third estimate that gets multiplied by, JUMP does this, recentered x1 and recentered x2. So the number of bidders minus 9.531, because that's the average number of bidders among all the auctions. So that difference times age minus 144.938, because that was the average age of all the clocks. All right, so you could use that expression, just plug in a particular age and a particular number of bidders, as long as it's not an extrapolation, and then you could predict the price. That prediction expression is going to give you a very good estimate, because if you look at the summary of fit for this interaction model, this is a very good model. We're explaining over 95% of the variability in the price. And after adjustment, it's about 94 still about 95%. Our root mean square error is down to 87.5, so our predictions are usually only off by $87.50, which among these clocks that cost, on average $1,325, is a pretty small amount of prediction error, it looks like. All right, so this is a very good model. That does it for this video. So make sure that you can do these things. And then video number 8 is the last one, where we look at a topic called multicollinearity.